Now that we've reminded ourselves of the vertex formula for the minimum of a parabola, or maximum if a is negative, let's apply this to optimizing a one-dimensional function. Well, our objective function isn't usually necessarily quadratic, but we could approximate it with a second-order Taylor polynomial like this, and then we could ask where's the minimum of that approximation, and maybe that's a good guess for where the minimum of our true objective function is. So go ahead and find the minimum of this second-order Taylor polynomial. So do that with paper and pencil. Pause the video if you have to. Welcome back from pausing. Let's take a look at what you probably did. You probably said, oh, this is basically like ax squared. There's like a, and time plus bx, there's b, and there's c. And so you can rewrite our Taylor polynomial this way. And then just use the vertex formula, plug stuff in. We get the 2 in the vertex formula ends up canceling the 1/2 from the Taylor polynomial. And we get negative f prime over f double prime. That's the location. Well, that's equal to x minus our current x position. So if we want to say what's the new x position going to be, it would be just based on wherever you are now plus that kind of update formula. So that is Newton's method for minimizing one-dimensional function. You do that once, then you get the new derivative and second derivative, and then do that again and just repeat that a few times. We haven't said how often really, but Newton's method, when it converges really quickly. It's always good to ask, did the units work out? And before, when we were doing gradient descent, we said the units didn't quite work out unless you did something funny with the multipliers. But this time they all work out, so I'll let you read about that in your own time. And then let's do a quick demo of what this looks like for one-dimensional minimizing. All right, so here we are. We've got a not purely quadratic objective function, and we want to find the minimum. And this is my current point, and we want to say, let's do Newton's method. So what do? Try drawing it, like copy this down on paper and sketch what Newton's method is doing and where it will end up after one iteration. So what it does is it says, let's go to the function here and do a second-order Taylor polynomial approximating the function based on the derivative and second derivative at this point. And a second-order Taylor polynomial is a parabola, so at least in one dimension. So based on the behavior of the function near that point, it draws the Taylor polynomial, which is this parabola, and then it will say, okay, that's the minimum of the parabola, so that's my new x position. So it takes this, you kind of think of that as on the x-axis, then finds the new Taylor polynomial based on the behavior of the function at the new x value, gets this new Taylor polynomial, then finds the minimum of that, and then says, okay, let's bring that back to, remember, we're really investigating the black curve here, and you can see there's a slight difference between our true objective function, the black curve, and a green function. That's our second-order Taylor polynomial on our third Newton step. But the minimum is getting pretty darn close to the true minimum, isn't it? Yep, pretty good. And then we'll do it again. And at this point, you can't even really see the differences. So that's what Newton's method is doing for one-dimensional minimization. Let's do some quick follow-up questions. What will happen if f is exactly quadratic? Think about that for a sec. Then the Taylor polynomial will be exactly the same as the function, the second-order Taylor polynomial. And so when you minimize the Taylor polynomial, well, it be exactly minimizing the true objective function in one step, which is pretty good. All right, so next time we'll talk about all this fun stuff in multiple dimensions.